Alright, so in this video I'm gonna be explaining another important paper with the title Taming Graph Kernels with Random Features. This ICML paper in 2023 by Kurmansky. We introduce in this paper the mechanism of graph random features. This is the random features of Ali Rahimi and Berst in 2008. Then people developed and generalized it for graph. Now this paper is using a different approach, but they introduced this graph random features their own, because there are many versions of that. So this is the Kurmansky version. The author is Kurmansky. GRFs can be used to construct unbiased randomized estimators of several important kernels. By the way, we use importance sampling to reduce the variance. It's a very classical thing. So when people say you have a big, your variance is high, then this is a good approach to tackle this issue. There are many things in machine learning that has a problem of variance. Even in reinforcement learning, the algorithm reinforce has a high variance. But there are many ways to reduce the variance. So let's carry on. So graph random features can be used to construct unbiased randomized estimators of several important kernels defined on graphs nodes. In particular, the regularized Laplacian kernel. So they provide means to scale up kernel methods defined on graphs to larger network. These graph random features address the notoriously difficult problem of cubic time complexity. Cubic, it means n to the 3. So we provide detailed theoretical analysis and extensive empirical evaluation. So we show that the computation of graph random features admits an embarrassingly simple distributed algorithm that can be applied if the graph under consideration needs to be split across several machines. We also introduce a still unbiased quasi-Monte Carlo variant of graph random features, this quasi version of that, relying on the so-called reinforced random walks that might be used to optimize the variance of graph random features. So as I said, Ali Rahimi and Resh, they introduced these random features. And the good thing is that we can have this relationship. The kernel is just the expectation of their dot product. This is amazing. Of course, the theory of random features goes back to Johnson. I have a video about Johnson-Lindström in my playlist for metric embedding. So random features provide unbiased, this low-rank decomposition of kernel matrix, effectively enabling the approximate computations with K to be conducted in subquadratic time by passing explicit materialization of K. So far, we have considered the points embedded in the regular Euclidean RD space, but what if the space itself is non-Euclidean? For example, upon discretization, such a space can be approximated by undirected weighted graphs. So several such kernels were proposed: diffusion, regularized Laplacian, p-step random walk, inverse cosine, even graph-led kernel, or even WL kernel. So many. Some of them are NP-hard, some of them are cubic. Unfortunately, most of the graph kernels, the computation of kernel matrix is at least cubic. So is at least this one. This is a major obstacle. A tempting idea is to try to apply random features also for graph kernels. What a tempting idea. Graph random features can be used to construct unbiased randomized estimators of several important kernels defined on graph's nodes, in particular the regularized Laplacian. So any special case of that is an important thing. Any special case of graph random. And we also introduced quasi-Monte Carlo variant of graph random features that relies on this reinforced random walks. So now we are ready to bring back the graph. We interpret U as a weighted adjacency matrix of the weighted graph. This U that we are talking about. So the result is the signature vector. They call it, if you go through this algorithm, what it returns is just a vector. It's a vector, phi of I. Because if you fix one node I, then you have this vector phi of I, this representation. And the load is also important. And if you simulate it, you will see that it creates a good representation, good structural properties. That's why they call it signature vector, because it's a signature of local structure of this node. Of course, you do it for all nodes. And so this algorithm 1 that I showed you here provides substantial computational gains in calculating this matrix, replacing the cubic time complexity with the linear one. Furthermore, signature vectors in practice can be often stored efficiently. There are also easy ways to directly control their effective dimensionality via one of two simple to implement tricks provided below. For example, this trick of anchor points. This technique samples randomly k less than n points from the set of all n vertices of the graph. We call this set anchor points. Another technique is signature vectors. The more algebraic approach to trimming the dimensionality of signature vectors is to apply this Johnson-Linder stress transform. So now we want to move from squared inverse matrices to graph kernels. So we consider this family of deregularized Laplacian kernels. And then the good properties of these kernels, so we skip them. And these are very good theoretical results of this kind of graph random features. So you see clustering errors for the experiments for the deregularized Laplacian kernel. Different test methods like regular graph random features with no compression, with a more accurate, and these techniques that I told you, these two techniques. And so we have proposed a new paradigm of graph random features for the unbiased and computationally efficient estimation of various kernels defined on the nodes of the graph. Graph random features rely on the families of random walks initiated in different nodes, depositing loads in the visited vertices of the graph. The computation of it can also be easily parallelized. We have provided detailed theoretical involving particular, This concentration result is also interesting in the appendix of this paper. You can go through the proof of this. And that's it.